All right. Hello, hello. Okay. So we're gonna get our second lecture. Ignore the stuff down here. It's from last one. I didn't update it, but pretty much we will be going over. We'll be going over like how the lidar actually perceives data, how we can interpret the data the lidar receives, and then like kind of working on like a simple algorithm that uses the data. So the simple algorithm we're working on is kind of like a pretty like basic ROS2 thing where you have like a car, and then when it gets close to the wall, it's supposed to like stop automatically by itself. It's called like an autonomous emergency braking system, or AEB for short. So first, let's go to like how the lidar actually perceives data. So a short introduction to the lidar is that we use a 2D lidar, which means it doesn't see three-dimensional. It only sees 2D, so on one kind of plane, and it rotates a laser at a high speed, and it discerns the distance to a surface based on the light reflection and how long it takes and stuff like that. And important, like although might seem obvious, the lidar only sees the front of objects. So like if you look at like a lidar kind of point cloud, it only sees like the front. So if there's something blocking, it won't see anything behind it. So that's just kind of something important as well. And it communicates with something called the sensor underscore messages laser scan. It's sort of like a laser scan message type. So what is this laser scan message and how can we kind of interpret it? So the main part of the laser scan message that matters is something called the ranges object, which is like a list in Python, which is like an array in other languages. And each number represents the distance in meters to the nearest object. So this is like an example of a ranges. So you might say like 1.2, which means like 1.2 meters to that thing, 1.2, 1.5, and infinity just means like more than 10, or like kind of a really big distance. So our lidar specifically has a 270-degree field of view. So how can we interpret this like inside of the ranges one? That means that the ranges will have 270 degrees of elements. And for our lidar has around 1080 elements, which means that the scanner returns a data point for every 0.25 degrees. So that means it has like a detail of around 0.25 degrees. So ranges like zero. So the first item in ranges will be negative 135 degrees. So that means like it'll look at the value negative 135 degrees, so around over here. And in ranges 540s will be roughly like kind of the center of what it's looking at. And in ranges 1080 will be 135 degrees this way. So it adds up to just 270. So although we know like specifically for our code like how many like elements the lidar has, like for our lidar, it's usually good practice to use like length message dot ranges if you want to like look at the center of it. So you can do like that over two to find like the center beam. So does this make sense? So pretty much like each object in the ranges is like the distance that the beam is taking to go from there to there. So now let's go over like some ROS2 like architecture and like syntax. So we discussed this last lecture as well, but ROS2 nodes are independent program or like kind of workers, and the automatic emergency braking system that we'll be making will like be its own kind of node. Subscribers are like topics that we want to subscribe to. So for our project, we want to subscribe to like the lidar data. So that'll be published in /scan. So we'll want to subscribe to /scan. Publishers are like topics that we want to publish to. So it's like stuff we want to write to. So for our automatic braking system, we want to like be able to stop the car. So we have to publish to /drive to stop the car. And then something, a callback function. We'll look at it more when we're talking about code, but it's like a special type of function that processes like it's like a function that's called every single time our lidar or like anything else that we're subscribing to processes like a new kind of scan or a new data point. So it's like pretty much run every single time the lidar has a new scan. So how does like a topic work? So topics have like various message types. So as we covered previously, like lidar has its own message type called like laser scan, and we can view these topics using a command called ROS2 topic list. And then we can also view individual topics by using ROS2 topic echo / topic name. So we'll look at an example here. So for this Ackerman drive, which is the type of message that is used for drive commands, it has a header, which is like a header object, and it has a drive, which is an Ackerman drive object. So you can kind of look at this closer here. So this is the Ackerman drive message. As you can see, it has a kind of a drive object, but like what is this drive object? We can look at the Ackerman drive object, and this has steering angle velocity, speed, acceleration, and jerk. So those are all the things that we can publish to that drive data point to be able to change the car. So this is just kind of another kind of description of what it is inside. Yep. What is the significance of flow 32? Flow 32 is just kind of like it just means a 32-bit flow. Okay. So instead of using int or something, they just use like our float, they just use flow 32 for like a 32-bit float. So we can also take a look here, let me try running something called a bag. A bag is kind of like a almost like a replay of like a thing that you did. So it's like useful if you want to like collect data after. All right, now we can do ROS to topic list, which was this command, and then that will show us all of the topics that are being published right now. So this is the Ackerman command, which is a drive command that we were talking about. This is odom, which we'll be using, but that's pretty much like the odometry. For this one, we didn't use the scan data, like in this when recording this back, so that's why you don't see any scan thing. But usually there would be like a scan here. And you have like the IMU, which is like the sensor that kind of detects speed and stuff like that. So the other command I said is you can use echo to like kind of echo a topic into the terminal. So let's do it with like odom. And then I'll resume this bag. And we'll see, it's kind of hard to see. Let's stop it. We have the kind of header here, which is like kind of its own object. And then we have the actual information. So we have position here. We have like orientation. And then we have linear velocity, angular velocity, and some covariance. So this is kind of how you can interpret everything. Yep.
So is that from like when you start the car at 0000?
Yeah. So like this is kind of just a bag. So it's like a recording almost. So I can like pause it and start it, and it'll kind of start updating like this. But usually when you're like on the car, actually, like you can access each of these individually, like so.
Yeah, but like when you're driving, how does it know that it's on?
Oh, how does it know?
Encoder or stuff?
It does it based on like where the stack is called, like where you call the main stack. So like that bring up launch pi command. Based on that, that's where it actually starts. That's where it puts 00 to.
Okay.
And then based on that, it like however much it travels, it uses that.
Well, how does it know how much it travels?
Oh, okay, okay. So it has like a IMU on board, which the IMU kind of
Oh, it does it
handles
for
that.
it?
Yeah, it does it for it. So this is just kind of like an example of a message type. So you have like the header here, which has like a timestamp, which is like the seconds and the nanoseconds, and then the actual information. So this is like the X position, this is the orientation, you have like the speed and stuff like that. And so that uses this kind of topic list command to list all the topics, and then you can echo a specific topic using this command. So for our autonomous emergency braking system, we first need to get our inputs. So we're going to be using /scan and odometry as well for the current speed, and we'll look more into that for the next slide. And then we're going to have to run logic on these inputs. So the logic is going to be, we have to calculate something called time to collision, or TTC, and we'll cover that as well in the next slide. And then we have to output if necessary, like if the TTC is too low, so that means the time to collision is too low, then we publish a message to the /drive with speed 0. So what is TTC? Like, why don't we just use distance? Like, why can't we just say, oh, the car is going here, and then when it's like 5 or like 0.5 meters away, it just stops. The reason why we can't do that is because if the car is going super duper fast, then it needs to stop earlier than if it was going really, really slow. And if you try to make a distance that works for both, you really can't, because if it's going too fast and it stops, then it could be like maybe a 5 meter distance or something, but then when it's going slow, it'd be like way too much for it to stop. So instead, there's this formula called TTC, and the top here is R, where R is the distance from the LiDAR, and then this negative R kind of with the accent on top is the range rate, which is represented as this which is the velocity. That's why we need the odometry times the cosine of the angle of the beam, which we'll get more into that later. And then for a threshold, usually like 0.8 to 1 seconds is like good. So like when it's like pretty much what that means is when it's 1 second away, stop. Like 1 second away from the wall, that's when we want to stop. So we'll just do like a quick code walkthrough. It's quite a lot, but I'll try to make it somewhat understandable. So first we have like this node, and then this is where we initialize all the variables. And then this is where we call the subscribers and the publishers. So here we have the slash scan, um, the slash scan subscriber. So we subscribe to slash scan, and then we call this, which is scan callback. And remember, I said this callback method is pretty much they run every single time we get a new scan. So, and then same here, we have something called ODOM callback, which is called again every single time we get a new ODOM measurement. And then we have our publisher, which is the drive publisher. So for ODOM callback, we want to pretty much set the speed of the car, which is like a global variable. We want to just pretty much update that. So whenever we get like a odometry thing, we're just trying to update, okay, like the odometry will just give us a speed, and we have to be like, okay, that's the speed of the car. Let's put that into our code. And then for scan, whenever we get a new scan, we want to also do all the logic as well behind it. So this is just like the math pretty much, like it uses NumPy arrays. So then we can like do it all at the same time without having to do each one individually. You don't really have to worry about the math. The main thing that's kind of important is here at the end, we're pretty much saying if the minimum like time to collision is less than our threshold, then we actually run the emergency brake command, and we get that minimum time to collision with all this math. So that's pretty much like the TTC formula right here. And then also we just use this logger function that pretty much just logs it to the console so we can kind of see what the TTC is and what it thinks it is. And then let's say that it's lower than our threshold, then we run that emergency brake command, and that's defined here, which what we pretty much do is we create a stop message, which this stop message is going to be this Ackerman kind of drive message. And we set the speed here to be 0. And we also set the acceleration to be -10, because doing that can kind of like make the car stop like faster. And then we also set a timestamp, which is just what this is. And then we publish this message with this command. We publish this stop message, and then this is just logging it. So even if you didn't have this, it would still kind of stop when it gets to that point. And this is just like your main function. I know I went through this pretty fast. Is there like any questions?
So are the messages just like a defined format or the protocol per se?
Yeah. So the messages will kind of we say it here. So let's say for this example, this Ackerman drive stamp command, that's the type of message that we have for slash drive. And there's like these really good docs, which I'll have a link to it by the end of the presentation. But this is this Ackerman drive stamp like message type, and you can look inside here. It has something called header, which if you look inside header, it's just kind of a timestamp and like a frame ID. But what we really care about is this kind of other drive command, which when we look inside this drive command, this actually has the speed and acceleration and jerk and stuff like that. So that's what we're doing here when we get to this point. We're doing stop message dot header. So now we created this, and now we're going to the header object here, and we're making the timestamp equal to whatever the clock is. And then we go to dot drive, which is this object right here. And then we're changing the speed object here to be 0. And then we're also going here to the acceleration right here, and we're changing the acceleration to be -10. And then that's kind of our object, and we're publishing this whole object to the slash drive kind of topic. So yeah, does that make sense? And then this logger function is just kind of to log everything like in the console. What this part does of the logger function, it just does it like every single second instead of like spamming the console. Just every second it does this. Same thing here. This happens like every 0.5 seconds instead of so it doesn't spam the screen. So yeah, and then also when you're making a ROS2 package, um, there's like a kind of a specific format that you have to follow. So this is kind of the package here, and then you'll have like, so this is like AEB is kind of like that uh the directory like located in SRC, and then when you go inside of that, you're gonna have like another directory called that same node name, and inside that directory you'll have like your init.py. This can just be empty, it just tells ROS that this is a package, and then you have the actual like logic, which is the AEB.py, and then you have another directory called resource, and inside of it you just have AEB, but with no extension or anything. It's just kind of empty. So this is it right here. And then you have like a package.xml, which contains information about like the package and like its dependencies. So what that means is kind of here we have to use Ackermann messages and like nav messages, sensor messages. So this just tells what the package needs to run. And a lot of this you can just like ask like chat or something to generate one for you. Like once you write the logic and stuff, it'll just generate like it for you. So you don't really have to worry about what goes inside here. The only one that I would worry about is setup.config or setup.py, which defines the entry point. So if you remember, when we call a command like something like if we call something like ROS2 run, and then we do like, let's say AB is our name, this second one right here is our entry point, whatever we put as a second command. So when you guys were doing GT follow the gap, you had something like GT follow gap, and then the entry point for GT follow gap was just GT follow gap again, right? So some packages will kind of have different entry points for different purposes. So for example, here is kind of where it's put here. So we have like AEB node is the entry point for this one, and that goes to AEB dot AEB. And what that means is just AEB, which is like kind of the header thing, and then it goes to dot AEB. So it goes to this file right here, and then it goes to the main function of this file. That's pretty much what it's saying. So when you have like, you might have like other code, like for example, if you make something like let's say follow the gap algorithm, where you have like one that's for small tracks and like one that's for like large tracks. You could have something like large tracks here, like large track, and then you could have something like small track here, and then you could define that what where each entry point goes in this setup.config file or setup.py file right here. So you could add another one like AEB other node, which this might go to like another file or another function that I might make. So it's like useful in order to kind of reduce like, instead of making a whole new package, you can use the same package for like the same thing. And then how do we actually go about, let's say we made this package and stuff. How do we go about transporting this to the car? I find like the easiest way to do this is just to use git. So like you go to the car and you go to like the source directory and you just do git clone, and then it'll just clone it into that directory, and then you can just use colcon build to build it, and then that's like the easiest way that I found to move stuff into like to move the package onto the car. So that's pretty much it. If you guys have like any questions, you can let me know. Um, One thing I was wondering though is like if you guys wanted to for the lab or something, if you guys wanted to try making like a AEB yourself, I could send like some documents or like kind of help guides as well, like inside the Discord. And maybe for like the office hours next week, we could try like publishing and running this AEB like onto the car itself. I was wondering if like you guys what you guys thought about that.
Yeah, it seems.
Yeah. So obviously my code will be there as well, like in the references. I put it here just in case if you want to take a look at it. But there are like uh kind of like almost like labs that you guys can access. So I'll probably send this, and it has like documents and stuff about like how they calculate this, like TTC function, the different kind of things that you might use, like this twist dot linear dot x for the speed to get the speed. And yeah, this one uses the simulator for submission, but we can just do it on the actual car. So I'll probably make like some type of Word doc or something that has like more deliverables and stuff like that. So but yeah, that's probably what I was thinking of doing, like making some type of like deliver will be like the AEB package, and then you could go through next week during office hours and just kind of try putting your package like on the car and stuff. So yeah. But if you guys want like any other like kind of projects or stuff, like I'm really open to suggestions. If you guys want to like make something like some other type of algorithm, I'm pretty open to like suggestions. So yeah. That's pretty much it for this lecture. I'll send like more information about how you can make the automatic emergency braking system in like the chat and stuff, and like resources that might help you when making it. Obviously, feel free to like talk to me as well if you have like any questions. Um, and then next lecture, so like next, not next week, but the week after next, we'll probably be talking about like getting the simulator installed. So that's like a pretty important part. Like if you guys aren't able to make it to the lab, or also just to like have development like be easier. Like the simulator is really helpful. It like runs on your computer, and then you can kind of make algorithms there, and you can run them like in your own time as well, which is pretty cool to see. So yeah, it just takes a while to kind of start up the simulator and stuff like that, but we'll probably do that next time. So yeah.
Take a while to start up every time, or like
No. Just like the first time, like installing it and all that stuff, it takes some time. But
we just write on like any PI file on our computer.
yeah, you can just write. I would like make a like a GitHub repo first, probably. And then I'd clone it onto your computer, and then like inside of it, just make sure to follow like this format. The kind of this format. So like you can name the you don't actually need to name the GitHub repository AEB. Instead, when you're like cloning it, you can do git clone AEB, and then that will pretty much like that'll just put it into an AEB directory, or make an AEB directory to put it in, instead of having you like instead like it could be like named anything. So like usually I'll do like an example. So usually when you make like a like do git clone and you paste it, it puts it into like a directory called the name of the directory. But when you're doing it in the source directory of like the cars, it usually doesn't like it when the name of the directory is different than the package name. So instead of having to rename your actual Git directory, you can just do git clone, and then again like the name. And is anyone like unfamiliar with how GitHub works or anything? You are? Okay. So GitHub, it pretty much is just a way to store like your code like on the website, and it makes it really easy because there's something called version control, which means that when you update something on here, you can like update it on your on your code, and then you can push those changes, and then in another computer that has your GitHub file, you can just do git pull, and it pulls those changes. So instead of having to like paste it in every single time, you can just do two commands, and it just essentially makes like the transfer way easier. So I could do like an example here. So when you do git clone, it just pretty much clones the repository. So whatever you have inside, like the repository is just like a file kind of. So this is my repository here with like the AEB, the resource, and then like all these files. And then what I did before is I just did git clone, and it cloned it into a file named the name of the repository, but the ROS doesn't really like it when the repository name or the name of the file is different than the package name. So instead, what we can do is just git clone like this, but then at the end, add something like AEB, which is the name of the package. And then when you do enter here, it clones it into a new file named AEB, a new folder named AEB instead. So now it's named AEB instead of being called like the name of the thing. So now if I go into AEB, you'll see here, like let's say on this one, I want to change like the entry point. Instead of AEB node, I want to just make it AEB package. So now once I have that saved, I can open the terminal, which is this, and then I can just do git add, which git add star just adds all the changes that you made to the git repository. And then once that's done, you can do git commit -m, and then space, and then like whatever you want your like committed message to be. So I'll just say changed entry point.
what a visual report that too. If you're on VS Code, the second icon on the left.
Yeah. This will also, yeah, if you want to use that, or you can also use GitHub Desktop as well. If you want another kind of way to visualize it as well, this can be useful. And then doing git push will kind of push it to the thing. And now when you go like to here, this has our older version. So I can show you by doing like, you can see this has the old version with AEB node, but we changed it to AEB package. But by doing git pull, and we do it again, you can see now it's changed to AEB package. So it makes it way easier when you're changing stuff to, instead of having to like put it every single time on the car, it's like all done through Git version control, which is very useful. And yeah, feel free to download like GitHub Desktop if this makes it easier. I know this is really helpful like if you're starting with GitHub. But yeah, and let me know if you have any questions as well. You might need to like install Git if you don't have it, but yeah, it should be pretty straightforward. But you can let me know. Anyone else as well can let me know if you have any questions with like the whole GitHub thing. But yeah, so yeah, it's all pretty much. Any other questions?
I don't know if this is kind of like a mechanical question, but when you, for the braking system, when you set the acceleration to -10, how how does it do that? Like, can you like just do that on a dime?
No. So what that's pretty much doing is this is like kind of like going into like how the Vesk works and stuff, but it just tells the Vesk like to stop like faster almost. Like it's not really necessary. You don't actually need to have that command. Like if I remove it, it would do the same thing. It's just kind of like it's just telling the Vesk like this is like a braking command like stop. But you could also just do speed equal to 0.0 and it would do the same effect. I also have like a video of it working, of it actually working. You can see I'm driving like pretty slow here, and then it stops pretty close. And then when I drive faster as well, you can see it also stops, but it stops sooner because I'm going faster. So that's kind of that TTC I work there.